I had a review. Well, hopefully we can go through these pretty fast. I asked first question, how do you design a full penetration weld? What's that? You don't. That's right. You just specify a full penetration weld, and they're required to look at the base metal and determine an electrode that will be sufficient for the job. So how do you find the capacity of a fillet weld? What's the equation? VPN equals what? Point what?
0.2.
Is it 0.2? 0.02.
The weld.
FEXX, the electrode strength. So grade 70, what do you put in there? Or sorry, in an E70 you'd put in 70 KSI. An E60 you'd put in 60 KSI. An E80 you'd put in 80 KSI. What else?
D and L.
DL. Okay, what's L?
L's length of weld.
The millimeters, right? No. Inches. Inches. The whole thing's in inches. Length of the weld in inches. What's D? The leg height is 1/16 of an inch, right? This is also assuming an equal-legged weld, which I highly recommend you always use. Okay? Not saying it can't be done, but there's a lot of weird fatigue issues that people often ignore or aren't aware of when they use a non-equal size leg height. Okay? Okay, so great. Yeah, that's the leg height, 1/16 of an inch. That's the length of a weld. And what? Now, this is kind of funny. What is this? This is assuming the weld is loaded in shear or tension. Shear. Well, how do you take into account if a weld's loaded in tension? What do you do? Give up. Is it conservative to assume the shear capacity for a weld in tension? Is it conservative to assume the shear capacity of a weld that's in tension?
Yes.
The answer is yes. Because we've done that for about 60 years. Okay? The last 5 years, people have started to try to take into account the direction with which the weld is loaded. Okay? They try to take into account if the weld is loaded in shear, then you go ahead and use this equation. If the load is welded in tension, what do you do? Yeah? How do you do that? Not the beta factor. Beta factor is something else. Some other way to do it.
Or an equation where it's either 0.85 RWL or 1.5 RWT.
So that's a little bit different. That's when welds are loaded, when welds are like this and being loaded, right? Where you have welds simultaneously in tension, in shear and in tension, right? And that's where you take into account, you have to have, you either use RWL plus RWT, basically the assumed shear capacity for everything, or you use the shear capacity, 0.85 times the shear capacity plus, was it 1.5 times the tension capacity? Yeah? Times RWT, tension capacity, plus 0.85 times RWL. We talked a little bit about why that is, right? You want things to be able to yield before they fracture, right? You'd like for that to happen, and welds are kind of brittle materials. But to go back to my original question, even above that on that same page, I said, how do you take into account or find the strength of something that's not loaded purely in shear? And you have to use that funny 1 plus sine equation. I mean, it's a funny equation that I can't remember, so I don't try to, right? But and what it does is it's basically working out more circle for you. It's basically working out this concept that if you know what the shear capacity is, you can find the tensile capacity, really similar to that 0.6 that we often use. But that 0.6 is when things are loaded, directly in tension or directly in shear, right? That equation allows you to do it for any angle. And I'm not sure why you would want to be able to do it for any angle, but engineers like to be able to calculate things, right? They just feel confident, and they can put a number on something. Great. So you'd use that 1 plus equation to figure out what the capacity would be, and then we did a little bit of review on this as well. All are fair game and good things to look out for homeworks or exams.
That's a modifier?
What's that?
That's a modifier? You multiply it by...
Yes, sir. That 1 plus sine theta is a modifier to this equation. It's a modifier to that equation. If you notice how that equation is defined when theta is 0, then that modifier becomes 1, and it's loaded in pure shear, and it's just this equation. When it's not loaded in pure shear, you calculate it as if it is in pure shear, and then you multiply it by the modifier, which should be greater than 1. And it should cap out at like, is it 1.4 or something number like that? Anyway, I don't remember. 1.5. Okay. Is everybody with me on that? Okay. The beta factor. What's the beta factor all about?
Reduction factor when you have long.
It's a reduction factor when you have really, really long welds. Okay? And I think it's actually when your L over your W is what they call it, or and W would be the pure leg height, which is I think is greater than or equal to 100. Okay? I think that's when it starts to take over. Okay? It starts to be less than 1. It starts to be a concern. So that means if I have a half-inch weld, which doesn't ever happen very often, that means it would have to be 50 inches long, right? 50 inches long. So this needs to be kind of something that you have built into your DNA, your steel DNA. That when you see a weld that's really long, you need to start sweating a little bit. Maybe you be thinking that beta factor might be important. Okay? Now, why do we have it? What's it for? Why do we fear long welds? It's very challenging to place a long weld without making imperfections in that weld. Extremely challenging. It gets sometimes hard to catch imperfections in really long welds. The other issue is that the stresses are higher on the beginning and the end of the weld, typically. And when we use this calculation, we're not quite assuming the entire weld is at its capacity, but it's a conservative assumption. Okay, there's a lot of conservatism built into bolts and welds. Okay, there's a lot of conservatism. Doesn't mean you need to push them. They're there for a reason. They're there because we don't want them to fail. Okay? Okay. Oh, hey, what is the maximum size fillet weld that can be placed in one pass? Something we didn't talk about last time that we should have. What I mean is if I have a plate here and a plate here, and I want to come and put a weld right there, a bead in the center between the two plates, what is the maximum size weld that I can place in one pass? 5/16. Some people will say 5/16 to 3/8. Okay, I often say it's in the ballpark. Depends on the welder. Why is that important? Why do we care? We're engineers. Why does that matter? We don't weld these things. That's right. Multiple passes. Well, we do care about these things. Okay, if you really think that way, that you don't care about that, then you need to change your attitude. All right? We're all in this together. Okay? We're all a team. Okay? And we need to try to design our structures to be easy to construct. Okay? It is our job to make it easy to construct. And if you can do something to minimize your leg height, to bring it down to 3/8 to 5/16, okay, by changing your length, it's not going to change other issues, then you should. Okay? It's much less expensive and much easier to construct a structure where you can do it in one weld pass as opposed to doing it in a pass, cleaning it all off, letting it all cool down, coming back, doing another pass on top of it, cleaning it off, letting it all cool down, and then coming back and having to inspect it. Make sense?
Another reason why you wouldn't want to go above 5/16 is it changes the inspection
inspection requirements on the weld.
It often does, and those inspection requirements are there for a reason. They're exactly there for a reason. You're exactly right.
Yeah, 5/16 is a part-time inspection.
Right.
5/16 is full-time.
That's right. And that's there for a reason. So 5/16 to 3/8, depending on which code you look at, is is about where the line is drawn in the sand. Do your best at all times to keep welds at or below 5/16 of an inch. All right. Okay, so I got this great question: why is field welding so expensive? You know, and some people will tell you it's not, but I really think it is. But why is it so expensive? Inspection services are very challenging, much more stringent. I mean, and it's because we're relying on those welds to carry heavy loads. They cannot have imperfections in them, and the reason why is because imperfection cause stress concentrations. Stress concentrations cause fatigue problems. Fatigue problems means something will fail suddenly under a load that it had seen multiple times before. Multiple times before. It's like a paper clip going back and forth, back and forth, back and forth. Eventually the paper clip's going to break. Okay, if you're moving it large enough. If you keep those deformations small, it won't break. You put a nick in the paper clip, it's going to break even faster. That's what we're talking about with these imperfections. Okay? Okay. Hey, we started this last time, but we didn't quite get to finish it. And I just want to, hopefully this is going to jog your memory a little bit, because this is our jump into eccentric connections here. If I had something like this, a cantilever beam with a load on the end, and I asked this question, I was like, what are the stresses? What kind of stresses do we have on this cross-section? And we said bending stresses, but we're going to not think about those anymore. Okay? What were the other stresses we have? Shear and torsion. Shear and torsion. And this is important. This is really important. When we talk about shear stresses on that cross-section, they're going to be large at the center, and they are going to be small at the edges, right? If we had to look at this on the side, it would actually look like a bubble. Or something like that. That's actually how mathematicians back in the 1700s first calculated things like J, the torsional coefficient. Is they thought of what if they found out the problem was very, very similar to a thin soap bubble being blown on a wire rim. It's the exact same. It's like that parabola is the exact same distribution of shear. Okay, distribution of shear on that cross section. Okay, so that's what it looks like. And then for torsion, what's it going to look like? What's it going to look like for torsion? Well, it's going to look like this. It's going to be high on the outsides, and it's going to be lower as it goes in towards the center, right? And it's going to be that way all the way around. All the way around. So if I want to find the stress, the combined stress, I have to add the stresses from this plus the stresses from this, right? Remember this? Yeah. If you don't, you better open up your strengths book, okay? Because that's something you should know cold by now, okay? Just be like, my name is, and then you're like, yeah, you add those stresses together. That's combined stresses, right? Well, would you add them all? I don't know. Here, these stresses will actually subtract from one another, right? And here, they would actually add to one another. Here, they're in two different directions, right? And here they're in two different directions. How about at the center? Well, there's no torsional stress at the center, right? But yet there's the highest amount of shear stress. These are all concepts. You should be able to boom, 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 boom. Now, why are we covering all this? Well, it's because this is analogous. This is some of the problem we've seen before. And this is analogous to the exact same thing we're going to be doing in bolts. And welds, we'll find out. Okay? Exact same thing. Any questions before we move on? Okay. So we had a handout that we started talking about last time. And I'm not going to go over the whole thing, but we went over this. This is the same thing we talked about before. We started talking about some of these things. And we started drawing bolt stresses, right? Bolt loads. Okay? Okay. So, I said, you know what? If I have a connection, and if I load it dead in the center, I know how to work that problem. I've done it hundreds of times before. It's easy. All my loads in the bolts look like this, right? Opposite direction, and what's the magnitude of each one of these loads? P over 6. We assume them to be all the same, right? Great. But now if I move that load, so it's not at the center of stiffness. Center of stiffness, yeah. I could actually find the center of stiffness of all these bolts, and it would be right there, right? Right there. So if I move my load, or for whatever reason my center of stiffness was moved because my bolts weren't symmetric, but if I move my load, and then what I'm going to be able to do here is I'm going to be able to put almost a shear stress on the cross section, and then almost like a torsional stress on the cross section, right? And if I do the torsional stress, I said the stresses would look something like this, right? They would be, you'd find your center of stiffness, right? You would go out from that point of center of stiffness towards the centroid of the hole, right? And then your force vector is going to be perpendicular to that point, right? We drew that for all the different force vectors. Oh my gosh, how embarrassing. That goes that way. That's the bottom of the arrow, right? Yeah, bottom of the arrow. Okay. Yes. Has to go in the opposite direction of the couple, right? Opposite direction of the couple. Now I ask this question. What is the magnitude of each one of these vectors? The magnitude of each one of these force vectors. What do you think? That's a hard question. Not a very apparent answer. We have to give more of a rhetoric answer. And the answer is that it's actually a function of the distance from the center of stiffness. Okay? At least elastically. Right? Elastically. That's the way we always work the problem, right? 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 Okay. So now I'm going to combine these loads, just like I was talking about combining these stresses up here. Okay? Remember when I was talking about, looking at different areas, adding them together? We're doing the exact same thing. So in a sense, this isn't even new. You've done all this before. Okay? It's just something you haven't done for a while and something you probably haven't done in quite the same way. Okay, so now I'm going to start adding these together, and I'm going to do my best to keep all my colors straight. I'm going to add vectors together. So I'm going to start out with these, because these are easy, right? These are really easy. So I'm going to basically transpose every one of these vectors down here. Okay. Now I have to transpose this vector. I have to add it. How do you add vectors? Well, you take the tail of your second vector and you put it at the head of your first vector, right? Yes? Okay. So, I'm going to take this vector and I'm going to add it here. And again, I'm doing my best. If it doesn't look like they're exactly the same, it's because I'm not drawing them correctly. But they are supposed to be the exact same. Okay, and now the cool thing is that now that I have these vectors, I have to draw the resultant. How do I get a resultant vector? What do? Tail to the first one, right? Tail of your last vector to the, from the head of your last vector to the tail of the first vector. Magnitude's going to look like that. That's going to give me the magnitude and the direction. The magnitude and the direction. Am I drawing this right? Hold on. No. I'm drawing it wrong. Drawing backwards. Okay, so now I'm gonna draw the resultants over here. That's supposed to be this vector. Not drawn very well. We'll say that's nothing. Or almost nothing. There's just a little dot. That's the dot. That's the vector. That dot right there. Almost nothing. Very low. So we would see that this is what our resultant loads look like. Okay? Here's our center of stiffness. And now which bolt is loaded the highest? What's that?
The one in the middle on the right.
How about that one and that one? I think it looks like it's the longest. I think the vector looks like it's the longest. Okay? So I'd say it's the worst. But we can see here that what we've drawn is that we're saying that this bolt is extremely highly loaded. And we're saying this bolt's got nothing on it. And this bolt's got almost nothing on it. Right? And this bolt's got not much on it. But these three are pretty highly loaded. The top two are the most loaded. Right? Right? And this type of idea and concept is what people use for a long, long, long time. Okay? We'll hand out a new set of notes and start talking about that. Okay, some of this we've seen before, some of this we've talked about, so I'm going to I think we're all kind of on the same page with this. We're saying again here at the top, I said previously we've always loaded our connections through the center of stiffness, or concentrically. We're not always this lucky. Hey, this is the one we've talked about 100 times before. Concentric loading, everything's loaded like this. Eccentric loading, this is the one that we just drew, right? Right? And we said that this was like some short, stubby one. This was long. This was long. And this was long. And this was long. And this is like nothing. Okay, that's what we came up with. We're going to do the exact same thing with welds. Okay, when we talk about loading it like this, we're going to have primarily shear on this weld and tension on this weld and on this weld, right? So we have some kind of stress here, we have some kind of stress here, some kind of stress here. And again, when we start talking about it being loaded torsionally, we would draw just like we did with the bolts, we would draw little imaginary radiuses that go out, and we would be in the opposite direction. So this would be up here, this would be up here, this would be down here, and this would be down here. You with me? And then we'd add these together to figure out what the force component was, and it would depend on the geometry to be what the true stresses would be. And this is how, I'm telling you right now, this is the way it used to be done. And it was painful with a capital P, because I did it. It was awful. It was tedious and horrible. And I'll just keep talking about it. If we assume that connections behave elastically, that's saying no yielding in the plates, bolts, or welds, and if there is no slippage, then we can say the forces from the moment on each bolt or weld is proportional to the distance from the center of stiffness. With this, we can derive the following. And now, these equations we used to derive. We used to look at what the torsion was and the distance to the bolt divided by the summation of the bolts squared. And oh my gosh, it was insane. And it's really similar to like MC over J, okay? Because that's what you actually use for a weld. You actually found a J, torsional coefficient for the welds, okay? And remember, this just gives us the moment component. Doesn't give us the shear component. Then we have to keep track of all the vectors, and we have to add all these up. It wasn't that big of a deal when we were doing it on this sheet of paper, right? It wasn't that big of a deal. It's kind of fun, actually, drawing around. It is a not very fun ordeal to do on very large, complicated connections. A lot of stuff to keep track of. You with me? But one thing here is that, we're talking about elastic analysis here. And we're assuming there's no yielding in the plates, the bolts, or the welds. Is this a good assumption? Do we have yielding in our bolts and welds? Yes. Do we have yielding in our plates? Yes. Is it conservative to assume that things stop right when they start to yield? Usually it's very conservative to assume that. Extremely conservative. And you've heard me talk about why engineers are scared of paper clips. That's why. Because paper clips are yielded to death, right? And we still use them all the time, right? Not that big of a deal. The assumption of the previous analysis is that everything must remain elastic. And that's what people did for a long, long, long time. These assumptions are far from what actually happens, but leads to conservative results. These techniques can still be used in connection design, but lead to extremely conservative results. Okay? So when we were out on our field trip, Scott Ambrose said, do you teach them the unified force method? Okay, and he used a different term that I'm used to using. Okay, but he's basically teaching them, do I use this inelastic connection design technique? And the answer is yes, we do teach you that. Okay? And he's talking about that the elastic was very hard and yielded very, very conservative connections, and the inelastic gets you more accurate, less conservative, but it's accurate, so it performs well. The elastic analysis assumes that all bolts and welds remain elastic. If we allow some inelasticity in our connection, that's yielding or slip, we will find that our capacity will increase. When a bolt or segment of weld yields, the connection doesn't fail. Instead, the load is distributed to the other areas of the connection. The connection will not fail until all of the resisting elements are at yield where the strain capacity is exceeding. What's this called? Structural resiliency, right? We'll stop right there and we'll pick up right here next time.